Hey everyone, welcome back to Calculus 3. This will be lecture 2 of the course, and in this lecture we're going to continue our work with vectors. We're going to move from 2 dimensions into 3 dimensions, and so we'll be discussing the spatial coordinates, space coordinates, and vectors in space. So when we say space, we mean 3D. So let's jump into it. Again, this will be section 1.2, space coordinates and vectors in space. Okay, so really up to this point in calculus, we've mostly been concerned with the 2D coordinate system, i.e. the plane. What we want to do now is we want to move calculus into 3 dimensions. Okay, and so for this, to accomplish this, we're really going to need the 3-dimensional coordinate system. Okay, so we'll be moving calculus into 3D, so we need the 3D coordinate system. Now, the 3D coordinate system is easy to work with when it comes to, points and whatnot. However, it does become quite a bit more challenging to visualize. And so I'll ask you all to bear with me as I attempt to draw the things that need to be drawn. But you can kind of think of the 3D coordinate system as, sort of having your x coordinate, which we'll write like that. And then you're going to have your x-axis, and then you'll have your y-axis intersecting the x-axis at a right angle, of course. And then perpendicular, you can think of that as the plane, right? And then, so for example, this might be the point 4, 0 in the plane. But there's a third axis to be interested in here, which we call the z-axis, right? Which kind of extends out the top of the plane. So if this point here is in the xy plane, then this would have coordinates 4, 0, 0, right? But if we want to move it a little bit up into the z-axis, up off of the xy plane, and off of 0 with regard to z, then it would be just up off top of this plane, and this coordinate here would begin to move off of 0, right? So this would be 4, 4. So far we've talked mostly just about things in the xy plane, but now things are going to get more complex because we're going to move out of here. So for example, a point up here would be the point 0 on the x-axis, 0 on the y-axis, and 4 on the z-axis. Right now, it's very challenging drawing any other points in here, just simply because of the limitations of 3D drawings. Particularly my ability to draw in 3D. So that's kind of the takeaway here. So the 2D system is just augmented with a third axis called the z-axis through the plane and the point, and it's perpendicular, of course, to the plane. Right, that means it makes a right angle with the x-axis, and it makes a right angle with the y-axis. Okay, so it's just perpendicular to the plane. Okay. All right. So many of the formulas and techniques that we establish for a 2D coordinate system, they can be applied directly to the 3D coordinate system as well. So an example there would be like the distance formula. Okay, the distance formula. So given any 2 points, given x1, y1, z1, and x2, y2, z2, the distance between them, is just calculated in the same way. So it'd be d equals, and you're just going to subtract x2 minus x1, square it, plus y2 minus y1, square it. That's the distance formula in 2D. But in 3D, we just have to add the third component, so z2 minus z1, square that, and then take the square root of that sum, and you get the distance between the 2 points. Okay, so for example, find the distance between 2, negative 1, 3, and 1, 0, negative 2. Okay, so d would just be equal to 1 minus 2 squared plus 0 minus negative 1 squared plus negative 2 minus 3 squared. Take that square root. And what do we get? We get negative 1 squared plus 1 squared plus negative 5 squared. Alright, so that'd be 1 plus 1 plus 25. And so the square root of 27. And so that's really the square root of 3 times the square root of 9, so 3 square root of 3. Okay. So, but you could, the point here is that you can see that this is 2D, and if we want to add, if we're talking about 3 dimensions, we just have to add in that last piece, that third coordinate. All right. Okay, very good. Let's talk through another example. We're trying to develop intuition at this point still. Kind of trying to develop intuition. So many of the formulas hold in 3D. They just have to be augmented with that third axis. Let's talk about another example here. So in the plane, we talk about circles a great deal. In this, in three-dimensional space, we talk about spheres. Okay, so a sphere with center x0, y0, z0, namely, okay, and radius r is defined as the set of all points x, y, z, okay, such that the distance between x, y, z and x0, y0, z0, okay, is r. So kind of similar to what we talk about with the circle, right? We say the circle with center x, y, and radius r is defined to be the set of all points x, y, such that the distance between the center and the edge is r, right? So it's very similar here, except it's just got that third coordinate in there. So using this, we can find the standard equation of a sphere. We can use, well, x minus x0 squared equals x minus x0 squared plus y minus y0 squared plus z minus z0 squared. That's the distance. We need that to equal r. Okay. And so we could write this slightly different by squaring both sides here, kind of getting rid of this giant radical. X minus x0 squared plus y minus y0 squared plus z minus z0 squared. That needs to be equal to r squared. Okay, this would be kind of the standard equation of a sphere. Okay. All right. So let's do an example with this. Let's find the standard equation of a sphere that has points 5, -2, and 3, and 0, 4, -3 as endpoints of a diameter. Okay, so what does that mean? Well, so you've got some sphere here. Okay, let's try to draw like some sphere. Now what we mean by endpoints of a diameter, that means you've got some line that cuts through the center of the circle, right? And one of the endpoints is this guy, maybe 5, -2, 3. And the other endpoint is 0, 4, -3, right? So the diameter is the distance across the sphere through the center. Okay, and so if this is the endpoint these are the endpoints of a diameter, then the length of this divided by 2 will tell us the radius, won't it? Yeah. So what we need to do is use this information to find the standard equation of this sphere. Okay. And so what we need to do first is figure out where the center of the sphere is, and we can use the midpoint rule for this. Okay, use the midpoint rule. Now remember, the midpoint rule, we've used it in 2D, and basically it's, if you want to know the midpoint between 2 points, you add up their coordinates and divide each by 2. Okay, and so for 3D, you just do it with all 3 components. Okay, and this is going to tell you, this will help us find this midpoint. Okay, so you can basically take the average of each of the coordinates, and that'll tell you the midpoint, right? So this would be 5 plus 0 over 2, and -2 plus 4 over 2, 3 minus 3 over 2. Okay, and so what do you get? You get 5 halves, and you get 2 over 2 is 1, and then this would be 3 minus 3. This should be a 3, so that'd be 0. Okay, so the center of the sphere is 5 halves, 1, and 0. Okay, so that's the center. Can we calculate the radius? Yeah. Right, the radius is just the distance from the center to one of the outer points. To one of the given outer points. So we can just use the distance formula to identify the radius. Okay, so let's do that. All right, so R is going to be equal to 0 minus 5 halves squared plus 4 minus 1 squared plus -3 minus 0 squared. That's square root. Now that's using, what does that come from? This is using the point 0, 4, -3, and the center point that we just found. which is 5/2, 1, 0. All right, so we're given this point at the onset. We use this point and the other point that's given at the onset to find the center point, and then the radius is the distance between the center and the edge, right? And that's what we're finding now. Okay, and right, so we can calculate this. And what do we get? We get, we're going to have, well, let's see, it'll be 5/2 squared plus 3 squared plus -3 squared. You square all of that, and you get 25/4 plus 9 plus 9. Right, and it looks like this would be 25 plus, what is that? 9 times 4 is 36. And I think you will get something like, oh, sorry, that should be a 4. Yeah. And so you'll get something like, I believe it looks like 97/4 square root. And so we'll call it square root of 97/2. Okay. So that's the radius. That's the radius. Now, given the radius, and the center of the circle of the sphere, we can calculate, or we can write the equation. Then the equation is x minus 5/2 squared plus y minus 1 squared plus z minus 0 squared equals, and then we want to square this, so 97/4. So that's the standard equation for this particular sphere that we're given. Okay. All right. Excellent. Okay, so these are just examples. We're building intuition using three-dimensional space, the three-dimensional coordinate system. So in space, in 3D space, vectors are denoted as ordered triples. We've kind of seen that, right? We've seen that. So in 3D, vectors are denoted as, v equals v1, v2, v3. Okay, the 0 vector, of course, is 0, 0, 0. Okay, and the standard unit vectors are, we have the I vector, which is 1, 0, 0, the J vector, which is 0, 1, 0, and now we have the K vector, which is 0, 0, 1. Okay, so we've got the K vector now in addition to the I vector and the J vector. Now notice in 3 dimensions, I and J have 3 components, not 2 components like they did in 2 dimensions. Okay, but otherwise they're the same. Okay, and we can also use the notation V is equal to, you can have V1, the V1 component times the I vector plus the V2 component times the J vector plus the V3 component times the K vector. Okay, so you've got all 3 of those now, right? You can write it like this. And so given this, most all of the other items that we discussed previously follow naturally. They basically just, it's almost exactly the same as in 2-dimensional space. So let's summarize what those things are, summarize what we mean. So letting U equal U1, U2, U3, component form, and V equals V1, V2, V3, and C is a scalar in R. Okay, so letting the, just going to start with that. Then equality. Equality means U equals v, if and only if all of the components are the same, naturally. u1 equals v1, u2 equals v2, u3 equals v3. Okay. All right, so that's the first thing. Equality means same as in 2D. It's just now you have to have the third component has to match as well, naturally. Secondly, component form. Okay, so if V is represented as a directed line segment, from P to Q, okay, so P is P1, P2, P3, and Q is Q1, Q2, Q3. Right? Then you can write V in component form by doing the same thing as what we did in 2D space. So V1, V2, V3, those are the components, and you can calculate them from your initial and terminal points as just Q2 minus Q1, Q1 minus P1, Q2 minus P2, and Q3 minus P3. Right? So you just calculate them just like before, right? That's what we had before, and now we have all three. All right. The length of a vector in 3D space, right? The norm of a vector in 3D space is the same as before, just now you have the third component. So v1 squared plus v2 squared now plus v3 squared. Take the square root. Okay. Okay, now what about the unit vector in the direction of v? Okay, unit vector in direction of v, so you'd have v over the norm of v, right, which we saw was equal to 1 over the norm of v times v, which is 1 over the norm of v times v1, v2, and v3. Okay, and this is, of course, just like before, it's for non-zero vectors. V can't be 0. Okay. What about addition? Okay, what about addition? Well, V plus U is V1, V2, V3 plus U1, U2, U3. So again, just like before, you add the components. So it's V1 plus U1, V2 plus U2, V3 plus U3. Okay. And scalar multiplication. Scalar multiplication works the same as well. So C times the vector V is CV1, CV2, CV3. Okay. All right, so those are most of the things that we discussed last time, and now we've just augmented everything to include that third axis, that third dimension, and we're good to go. Okay, so let's do a few examples here. Let's do an example. Okay, so let's example, find the component form. Okay, find the component form and length of the vector V having initial point -2, 3, 1, and terminal point 0, -4, 4. Okay, then let's find a unit vector in the direction of v. Okay. Okay, so we're given a vector v, we're given the initial and terminal points of a vector v, and we are asked to write it in component form and find the length of the vector, and then also find a vector in the direction. Okay, so we can make quick work of this. So v is equal to, right, so v1, v2, v3, those are the components. How do we calculate them? Well, we subtract the corresponding coordinate from the terminal point and the initial point, right? So we would subtract, you'd think of it like this, q1 minus p1, q2 minus p2, q3 minus p3. Okay, and so in our case, and that's going to be the vector actually. Okay, so in our case, it's going to be 0 minus -2, comma, and then it's -4 minus 3, and then it's 4 minus 1. Okay, and so you should get 2, -7, and 3. Okay, so that's the component form of v. Now we want to find the length of v, so the norm of v. And that's going to be 2 squared plus -7 squared plus 3 squared. Right? Just squaring each of the components, adding them all together, taking the square root. And this is going to be 49 plus 9 plus 4, so you should get 62. Okay. And finally, let's look for a vector that's in a unit vector in the direction of v. So remember how we did that. We said u is equal to the vector v divided by its norm. That's a unit vector in the direction of v. Okay, and so that's equal to 1 over the norm of v times v. And so we can just put these things in here. That might be the best way to represent it, actually. All right, you could naturally move the square root of 1 over the square root of 62 into the vector components, but I think it's fine to leave it like this. That's still a vector. All right, very good. Okay, let's keep moving here. Let's keep moving. What does it mean for vectors to be parallel? Okay, so definition, 2 non-zero vectors, u and v, are parallel if there is some scalar c such that u equals c times v, right? Such that one of them is equal to the scalar times the other. Okay. All right, let's draw a picture here. Okay, so let's draw a picture. Let's put our v in here first. Okay, and then let's put in another one here. We'll call this W. Okay, and then we'll put in another one yet. We'll call this guy U. Okay, so these vectors are all parallel. Okay, you can see that they're parallel because I've drawn them in the plane, and it's kind of obvious. But using the definition, you could say that it's probably the case that u is equal to 2 times v. Okay, whatever v happens to be, if we double it, you might get u. And w looks like it's going in the opposite direction, so it's equal to negative v. Okay. The point here is that multiplying a vector, so two vectors would be parallel if they may differ in length, they may differ in position, but so long as one can be multiplied by, so long as there exists some scalar c such that when multiply one you get the other, then they must be parallel, right? So the definition here says that they're parallel if there's some scalar c such that you can make them equal by using a scalar product on one. Okay, and so you can kind of see that here intuitively. Okay, here in the 2D plane, it's easy to see that these all have the same slope. This one is going the wrong direction, but we can make it equal to v by multiplying times a negative, and this one is much longer. We can make it equal to u by multiplying v by 2, or having u and and so that's the idea. That's the idea with this definition. All right, moving on. Let's do an example here. So vector w, vector w has initial point 2, -1, 3, and terminal point -4, 7, 5. Is u equal to 3, -4, -1 parallel to w? All right, so you've got some given vector and another vector u. Are they parallel? Is v equal to 12, -16, 4 parallel to w? Okay, so we got to test some things. So first, let's write w in its component form. So w is going to be equal to -4 minus 2, and then 7 minus -1, and then 5 minus 3. Okay, and so you should get -6, 8, and 2. Okay, so right off the bat, you can see that 2 times u, right, is equal to w. Right, so 2 times u, 3, -4, -1. Right, so that's 2 times 3 is 6. 2 times -4 is -8, and 2 times -1 is 2 times -1 is -2. Right, so 2 times u is not quite equal to w, right? But you'll notice the signs are all flipped. So -2 times u is equal to w. So it'll be -6, 8, 2, which is w. Right, so we can see that, basically this implies that u is equal to -1/2 w. Okay, so u is parallel to w. What about the v vector? Right, so what about v? Well, so we've got, 12, -16, and 4. That's v. And we want that to be equal to c times our w vector, which is -6, 8, and 2. All right, that's what we want. We want to figure out if there's such a c exists. So what we can do is we can set set up kind of a, and I know we haven't, I'm assuming nobody's had linear algebra, you can set up kind of a system of equations to use this, even though like we haven't really talked much about systems of equations yet. But what you could do is you could say 12 needs to equal c times -6, and -16 needs to equal c times 8, and 4 needs to equal c times 2. Right, that's kind of what we need to have happen. There needs to be some c which makes all this work. And so that means c is going to be equal to 12 over -6, which is -2. And c is also needs to be equal to -16 over 8, which is -2. And c needs to be equal to 4 over 2, which is +2. Okay, so no such c. We got the -2, but this one's a +2. All right, so well, all that means is that there's no real number c that's going to make this work, and therefore, so there is no c in R such that v equals c times w. So what does that mean? It just means that v and w are not parallel. That's all that means. Okay, it's just a quick way to test it. Kind of break it down like this and figure out what c would need to be to make it work, you know, and if basically if the requirements are consistent across all three components, great. If not, it doesn't work out. All right, very good. Let's do another example. Again, kind of just trying to bridge the transition from two-dimensional space to three-dimensional space, kind of trying to develop some intuition about 3D space. So let's determine if the points, I'm going to write them here, P is 1, -2, 3, Q is 2, 1, 0, and R is 4, 7, -6. Determine if the points, these points, all lie on the same line. How do we do that? Well, what can we do? Well, what we can do is there's a handful of ways to solve this problem. I think the way that we'll solve it is we're going to translate these points into two lines, right? First, we're going to talk about the line PQ, right? The line that starts at P and ends at Q, right? And let's write that as a vector. So that'll be 2 minus 1, 1 minus -2, and 0 minus 3 as a vector. And so you get 1, 3, -3. Okay. The second line would just be same initial point, but the different endpoint. So PR. Okay, so now it's going to be 4 minus 1, 7 minus -2, and -6 minus 3. And so there we get 3, 9, -9. Okay. Now, the way to think about this is that you have, and I'm going to draw this in 2D, but if I have two vectors and they both have the same initial point, okay, so we'll call this P, right? You can see both lines, these are vectors now, both lines have the same, these are vectors with the same initial point, right? And so if they have the same initial point, that means the tail of the vectors are the same, right? Now they're parallel, right? Are those two vectors parallel? No, they're not, right? But when would they be parallel? So these two vectors have a common initial point. This would imply that they lie on the same line if they are parallel, right? So remember, that's what we're trying to figure out. We're trying to determine if they lie on the same line. They're going to lie on the same line if they're parallel, right? These are not parallel. They have the same initial point, but they will lie on the same line, right? That's PQ. PR is going to start there, and if it's parallel to PQ, it's going to do the exact same thing, right? So PQ, PR. They'll lie on the same line if these two vectors are parallel, given that they start in the same position. So all we got to do is test to see if they're parallel. Does that make sense? This will imply that the points are on the same line since they have the same starting point. Okay, so that's, hopefully that makes sense. All right, so we just need to test these 2 points. All right, so remember PQ is 1, 3, -3. PR is 3, 9, -9. Right, so I can kind of tell you by looking at those, it looks pretty good. But let's set it up our way. So we basically need we want, this times some c to equal that. So 1 times c equals 3, 3 times c equals 9, and -3 times c needs to equal -9. All right, so that means that c equals 3, c equals 9 over 3, which is 3, and c equals -9 over -3, which is also 3. So yes, they are parallel because PR equals 3 times PQ. Okay, so they're parallel. Okay, and that means, therefore, P, Q, and R must lie on the same line. Okay, they must lie on the same line because we built vectors out of these two with the same initial point, and we found that those two vectors were parallel. Okay, very good. All right, and let's do a couple more examples, and then we'll say we're fully acclimated to 3D vector talk. Okay, let's do another example. Let's write a vector given, okay, let's write, let's see, v equals 4 times I minus 5 times k. Let's write this in component form. Let's make sure we understand how to do this, and that 3D vectors aren't throwing us for a loop on this one. All right, so what does this mean? This means 4 times the vector 1, 0, 0 plus 0 times the vector 0, 1, 0 minus 5 times the vector 0, 0, 1. Okay, this is your I, j, and k, right? You think of those as scalars. Okay, and so can we do this multiplication and addition? Yes. So this is 4, 0, 0 plus 0, 0, 0 plus 0, 0, -5. And of course that's 4, 0, -5. That's how it would work, right? But you can pretty much jump from here right to the finish line. Once you've done this a few times, you'll see, oh yes, it always kind of works out the same, doesn't it? Okay. All right, so that's another example, 3D vector. Moving out of the standard unit vector form into the component form. Okay, kind of going the opposite direction of what we've done in the past. All right, let's do one more example. Okay, in this example, let's find the terminal point of the vector v equals 7i minus j plus 3k, given that the initial point is p, and then it's negative 2, 3, 5. Okay, so we're told what the vector is. We're given the vector in component form. Well, not component form. We're given a vector as a linear combination of the standard unit vectors. And we're also told what the initial point is. But we're not given the terminal point, obviously. That's what we're looking for. So for this, right, so we need to find Q, right? This is going to be your Q1, Q2, Q3, such that, right, we need to find this terminal point Q such that the vector V is equal to, well, the directed line segment PQ, right, which will be equal to 7i minus j plus 3k. Right, so we're kind of building it up using the reverse kind of thinking. Right, and so that's going to mean that we need, right, so that implies what? It means Q1 minus negative 2 needs to equal 7. Right, so this guy minus that guy needs to equal this guy. And Q2 minus 3 needs to equal negative 1. Right, so this guy, Q2 minus P2, needs to equal negative 1. Okay, and finally Q3 minus 5 needs to equal 3. So Q3 minus P1 needs to equal the component 3. Okay, and so these are really easy to figure out. You know, you've got Q1 equals 7, and this would be plus 2 over here, so it'd be minus 2, so it's 5. Q2 is going to be equal negative 1 plus 3, so it's 2. And Q3 would be 3 plus 5, so it's going to be equal to 8, right? So the terminal point is 5, 2, 8, right? We could check that, right? We can check that by, you know, basically taking your terminal point Q, 5, 2, 8, and subtracting off P, negative 2, 3, 5, and you better get the original vector that you started with, right? So we can double check that. Okay. All right. Well, I think we'll leave it at that. This is, again, you know, this section is all about moving into 3D, right? So we're kind of gently moving into three-dimensional space, right? So we started with 2D vectors, defined what a vector is, what all the properties of vectors are, and then we took those and we moved into 3 dimensions, and we've done a few examples to kind of acclimate ourselves to the kinds of thinking that is needed when working in 3D space. And don't worry, there'll be lots and lots of more examples of three-dimensional problem solving. But that's going to do it for this one. The next lecture will be, we're going to move into the dot product and the cross product. Up next will be the dot product. And then after that, we'll talk about the cross product. And so these are special operations that can be done on vectors. And we'll get into all of the details of what they're about, what they're good for, and we'll use them throughout Calculus 3, all over the place. They get used all over in mathematics, period. So, all right, well, we'll leave it at that, and we'll see you all next time. Take care.